Hello, everyone. Are you okay? So welcome to the 26th International Congress of Mechanical Engineering. My name is Denis Fernando from UFABC, or Federal University of ABC. That's my work. So my work together with Professor Reinaldo from UFABC 2, from Professor Ricardo from the Institute of Aeronautics and Space from São José dos Campos, and Professor Bruno Carmo from Polytechnic School of University of São Paulo. The title is a numerical study of a supersonic separator with curved supersonic nozzle. The scope of our presentation is the introduction of this problem, right? Some objectives, so the main objectives from this work, a theoretical foundation and some methodologies that we used in this work, the results, and a discussion about our work, some conclusions, and future works, okay? So, a briefly introduction about supersonic separators. What kind is this device? A supersonic separator is a divergent convergent nozzle used to expand a gas adiabatically, thus extracting heavy components due to the condensation from this, due to the temperature drop in the supersonic section, right? Therefore, a fluid of the nozzle outlet is filtered from these heavy components, okay? So our objectives from this work is investigate the influence of curvature in the convergent-divergent nozzle in relation to the straight simulation, the straight nozzle, the straight section, right? And compare the flow behavior. So localize the velocity fields, acceleration fields, Mach numbers, pressure fields. So our theoretical foundation from this problem, we did from the parameterization of the curve. This construction will be given from the g-force. The g-force is the ratio from the acceleration of the body or the fluid, the acceleration of gravity, okay? So if we open from a circular shape, we can, from a given velocity from a straight section and a g-force number, we can reach a radius from the arc of the geometry, okay? So we found from the straight section a 466 meters per second, and 100,000 G was the finite value from the velocity and the g-force, using air as working fluid, okay? So the methodology is using the ANSYS workbench in order below. So space claim to build a CAD from our geometry, the ANSYS meshing to create and redesign the mesh, the code ANSYS Fluent in some conditions. So we used the Finite Volume Method, okay, from this work. Pressure-based is a segregated solver from CFD studies, right? The flow is compressive, and we used ideal gas model from the air. And the turbulence model, we utilize runs. At least K-epsilon RNG is the model that we used, okay? Then also geometry. So according to g-force formula, the radius from our inlet values is 0.221 meters, and the angle is 63.42 degrees, okay? And we increase the length of the diffuser 1.5. From the mesh, we done a study of mesh, okay? We did a mesh study, 52,200 cell volumes is a value acceptable that the velocity field doesn't shows change from the number of the cells. Okay, so that's the convergent section, the throat of this of our nozzle, the supersonic section, and the inlet of diffuser section. Okay, good. The boundary conditions from our simulation is 100,000 Pascal to inlet and 6,500 Pascal to outlet. Okay, and to 291 Kelvin to total temperature. So it's okay, our simulations. And the results, the static distribution, so has a drop of pressure fields, and almost in 3 meters we have a shock, now normal shock, and the pressure is stabilized from this work. Okay, 770,000 Pascal. So the Mach field, right? Do a mean Mach number in the middle of this nozzle, we can reach some 1.7 in the simulation is very similar with the straight case, at least. Okay, and the G-force field with parameters for 100,000, 118,000, okay, G from 95,000 G, okay, and some oblique shocks are reflected in the middle of the curved nozzle. So, main analysis from the initial velocity is from we can reach some Mach numbers. So we can reach higher Mach numbers in regions that we have lower radius. Okay, so and this is it can be visioned in the red of figure 9 or figure 8 or figure 7. Okay, so but the difference in Mach value has a cause of effects of the centrifugation, where the gas is pushed to the outside of the nozzle. So the inner part with a lower radius has the gas becomes more rarefied. So the Mach, the expansion of the gas is greater, the Mach number is greater too. Okay. On the other hand, the external region of the curve with larger radius, the gas is more compressed due to centrifugation, so the Mach number decreases. Okay, the conclusion and future works from our work. The numerical results were successfully achieved. The most important visual data being the fact of deflection of the one side of the nozzle due to the effects of deceleration of the gas, right? The supersonic conditions for the flow were obtained. Our reference, questions and contacts. That's my email, my telephone. Many thanks to PolyUSP, UFABC, and RCGI for the research opportunity, and the FAPESP and Shell Petroleum. And that's it, okay?